Introduction of vectors. So, if we have a quantity that is just described by its magnitude, that's called a scalar, like distance and speed. But if we have a quantity that is specified by a magnitude and a direction, that describes a vector. So, distance, I traveled 2 kilometers. You're like, oh great, good for you. If I say I traveled 2 kilometers north, now you know a distance and a direction that I went. So 2 kilometers north would be an example of displacement. Just distance would be 2 kilometers. Same thing with speed and velocity. Velocity actually has a direction connected to it. So I want you to look through these and put an S for scalar, V for vector, and some of them might be neither. How did you do? Scalar, scalar, vector, neither, vector, scalar, neither, vector, vector. Any questions, complaints, discussions about any of those, or do they make sense? All right. How do we draw vectors? How do we represent vectors? Vectors represented with a straight line and an arrowhead. Sometimes that arrowhead's like in the middle, sometimes they put that arrowhead on the end. I usually put arrowheads on the end just because it feels weird to put an arrowhead in the middle. And our first definition here is a position vector. It always starts at the origin and goes to some point. So if you have the coordinates x, y, you have a position vector. Now, instead of writing them as coordinates like this, we write vectors as column vectors, with the x coordinate on top and the y coordinate on the bottom. And you'll see different textbooks write vectors in different ways. Sometimes they write it, the IB textbooks used to like to write it with a bold letter. Problem when writing in your notes is how easy is it for you to write in your notes in bold? You just like go over top of it so many times to make it really dark. So then often you'll see a vector with a little arrow above it, or sometimes underlined. And sometimes you'll see me, I don't know if this is official or if I just did this when I was lazy in university, but I'd often just do it with one arrowhead. I don't know why, because maybe I could just draw it all at once instead of having to lift my pencil and draw another arrowhead. I'm not sure. Maybe that's official. Maybe my professor did that. I don't know. But I often draw them with just like a half arrow over top. So if we had the point A, 6, 3, we could write that as a column vector, 6, 3. And I talked about the vectors being written as lowercase bold letters. Sometimes you can also do the endpoints, O to A with the arrow over top. Or we can underline them. I like the arrow over top. Or the half arrow. Bunch of different ways of showing you have a vector. if you have a column vector, the top is your horizontal, the bottom is your vertical movement. So we have the points 1, 2, and 3, 6 on the Cartesian plane below. If you wanted to go from A to B, does it make sense that you would have to move 2 units to the right and 4 units up? So we could represent this movement by the column vector. A to B is 2 units to the right and 4 units up. B to A would be 2 units to the left and 4 units down. Not too hard, not too crazy. We're going to do all of the math of grade 10, like y equals mx plus b, with vectors. And then we'll be able to do math in 3 dimensions with vectors really easily. Whereas our previous math with 3 dimensions gets a little bit complicated. So you're going to see where this is really, really useful. Another definition. A unit vector has a length of 1. And you can add arrows over top of these if you want. Standard unit vectors are 1 to the right and 1 up. And that allows us to write any vector in terms of its unit vector. And this is called unit vector form. Because the vector 2, 4 would be 2 to the right, 4 up. So you could write 2i, because I is 1 to the right. And you're going to do that twice. And 4j, and j is 1 up. And you're going to do that 4 times. And here's a picture showing that idea. So I'd like you to do the next question. All of these, write them in column vector form and unit vector form. And you can check your answers here when you're done. So in 3 dimensions, we add a new unit vector, k. So now we've got x, y, and z, so we have 3 things that are column vectors. And our new vector k would just have z, which in 3 dimensions you have your x, y sort of on an angle here, and then z coming straight up. So if you wanted to draw the vector on 2-dimensional space on your paper, we would go 3 in the y direction, -9 in the x direction, and from there you can sort of make a rectangular box that's in that 2-dimensional space, and then you go up 4 units, so this length up to 4 is the same as you would have to go up 4 from that corner, and there's your vector going -9, 3, and 4. How's that for visualization? Okay, so here's the idea. Maybe I'll draw it out in slow motion. Normally we just have x and y, right? But you take your x and y and imagine drawing that on 3 dimensions as if someone had put it on a table. Can you see this is still at 90 degrees then? Can you visualize that? So then when I have -9 and 3, well, -9 would have been here, and 1, 2, 3 would have been there. And if I follow that same, that would be the -9, 3, like I would have over here. 4 has to go, here's your z-axis, straight up and down. You count 1, 2, 3, 4, and that distance, 1, 2, 3, 4, is where your point is going to have to end. Starting at the origin then and going to that point is a three-dimensional picture of your shape. I think the one that I did on the computer is quite a bit nicer, but that's the idea. Your x and y coordinate got laid flat, and you go straight up and down for your z coordinate. This would be the point -9, 3, and then you go up 4 units from there. And this would be the point as a column vector, -9, 3, 4. Now we get into some math. Yay! We've just been defining things. Once we get into the math, it's a little bit more exciting. The magnitude or modulus of a vector is how long it is. And you can calculate it with the Pythagorean theorem. A squared plus b squared equals c squared. So if in 2 dimensions, I had the vector 6, 8, that would mean 6 to the right, 8 up. How long is that vector? Do you recognize this as a special 3, 4, 5 triangle? 3, 4, 5, 6, 8, 10. But you could still do a squared plus b squared equals c squared if you wanted. So that vector has a length of 10. How would you figure out 3 dimensions? Okay? And this is actually, I think, really, really cool. I'm going to erase some stuff. I'm going to work through the 3-dimension stuff. Can you see in 3 dimensions that if I wanted to find this, that if I connected here and here and here, this would be a right-angled triangle? And this part is the hypotenuse of that right-angled triangle? Okay. So in the green part, this was my x, this was my y. Would you agree with a squared plus b squared equals c squared that the hypotenuse here would be the square root of a squared plus b squared, just x squared plus y squared? This is my z. So now I'm going to need to do a squared plus b squared equals c squared here. And what's really cool is this will then be the square root of this side squared, which just gets rid of your square root sign, x squared plus y squared, plus this side squared. That's so cool that your a squared plus b squared formula just becomes like a squared plus b squared equals plus c squared. And if you went to 4 dimensions, you'd have a squared plus b squared plus c squared plus d squared in a square root. And you could just keep going. Drawing in 4 dimensions, though, that hurts the brain quite a bit. We won't do that. But there's your length in 2 dimensions, and here's our length in 3 dimensions. And when we want to find a length, we use the same thing as absolute value bars, because absolute value bars are just in 1 dimension, how far a number is away from 0. And now we're finding lengths in 2 dimensions and in 3 dimensions. vectors used to be part of the IB curriculum. And they would have written out the formula this way. I like the x squared plus y squared equals z squared better. After AP, you're like, what's a formula book? What is that? So, question at the bottom, can you find the length of negative 934? Are we allowed calculators? There'll be some stuff that will calculate, for sure. All right, how did you do on this one? Did you get the square root of 106? What did you need to go back and put one? And you can do the next two questions as well. I'll put the answers up for these ones so you can see if you get them. And C is super cool because it's a nice whole number. And how did you do on this one? First of all, we know that the length of V would be this. If we made it equal to 10, we could square both sides and solve. And A would either be positive or negative square root of 42. So a unit vector can be in any direction, not just the direction of the axes. So we put a little hat on a vector, and that's its unit vector. So if I have the vector u, 6 to the right, 3 down, and 2, if I use down, I can't use up again. Oh, it's 3 dimensions. I would like someday, and have a smart board, right? Can you imagine like this holographic teaching? I could just like draw things in 3 dimensions, and they have that in movies, so they should have that for teachers soon, right? It's too far away.
I don't know, I'm sure it's just in a few years.
Can't be too far. No. 1, find out how long u is. And this was one that we did earlier, right? That worked out perfectly to 7. 2, take your regular vector and multiply it by 1/7. Because if you multiplied it by 1/7, its length now would be exactly 1. And then 3 different ways you could write it. This is my favorite. I like the 1/7 out in front. Keeps the regular vector there. You could distribute that 1/7 inside, or you could write it as with unit vectors. A whole bunch of different ways of writing the same thing. You know what's going to cause you frustration? Is if you write a vector and forget the arrowhead over top, or underline it, or show that it's a vector, it's like a half a mark mistake. So our formula for the unit vector is always going to be 1 over the length of the vector. Because if its length was 7, and you chop that up and divide it into 7, you'd get a length of 1. A whole bunch of different ways you can write the same thing. So try number 9 and 10. I'll put the answers up in a second. Number 9. And again, I like it with the 1 over square root of 29 out in front, but you could distribute it in. You could rationalize it. You could do a whole bunch of extra math not needed. And here's number 10. So if you wanted a vector with a magnitude of the square root of 7 in this direction, well, 1 could write your column vector, find the length of that column vector, and then we would know that its unit vector would be this. But you could distribute it inside. I'd leave it out in front. And once you have the unit vector, you just need to multiply by the square root of 7 to get your actual vector. So I probably would even, my favorite way to write this one, I'd keep the 5, the negative 3, and the 2. Then if you multiply by root 7, you'd have root 7 over 38 out in front. And now you have the same direction that you started with, but you have a new length. I can scroll back up. How about that? Properties of vectors. Two vectors are said to be equal if they have the same length, same magnitude, and same direction. So if these two that are parallel, it doesn't matter where they start and where they end. So vectors are kind of free-floating, which is part of what makes them powerful mathematically. So A to B and C to D start at different places, end at different places, but we say that those vectors are equal. Because both of them go, 4 to the right and 5 up? That sure looks like it. So they would be both written as 4, 5. Even though they start at different places and end at different places. If we're going in the opposite direction, then one is the negative of the other one. So D to E looks like it's 6 to the right, 2 up. And G to F would be the negative of that. It's 6 to the left and 2 down, which is the same as negative 6, 2. So you'll see when you have a number out in front of a vector, it multiplies everything inside that vector, like a scalar does in matrices. You'll start to notice some of the rules of matrices kind of follow and do the same thing for vectors. Number 3, if you multiply a vector by a scalar, the resultant is another vector parallel to the first vector, because it has still the same direction, but it's just bigger or smaller. So are these vectors here parallel? If they're parallel, one of them is a multiple of the other one. So these ones would be parallel because A to B is 4, 5, D to E is 8, 10, And there is a value of 2 that if you multiply the first one by 2, you get the second one. Now, how did we tell things were parallel in the past? We think back to like two-dimensional math. That's when you did 2 lines were parallel. What would you have to say? The slopes are the same. Okay? So in a vector is very much like a slope, right? But it has rise over run. The slope of this one is 5 over 4. The slope of this one is 10 over 8. How would you tell that they're the same? Well, you would reduce your fraction, right? To lowest terms, and you'd see that they're both 5 over 4 when you get to lowest terms. So we're going to have vectors, and they kind of act like slopes. But we still just write the x value on the top and the y value on the bottom. So write each of these vectors in terms of A or B. How are A and B related? So there's A, and there is B. And if we would look at C, which is negative 6 comma 3, you could, well, I want to do this here. I'm going to take A, I'm going to draw over top of it in a green arrow. I'm going to draw over top of B in a purple arrow. And I'm going to clone those. Oh, not that way. I'll clone this way. Infinite cloner. Purple one. Make it an infinite cloner. And C happens to be negative 3b. So if I took 1b, 2b's, and 3b's, it matches up perfectly with C, but in the wrong direction, so I'd have to make it negative. If I would look at D, well, D is definitely in the same direction of A, but I would have to cut it in half. So it would be half of A. E, 1, 2, 3, 4, 5 B's in the opposite direction, so it's negative 5B. But if you counted out E at negative 10, positive 5, and then you wrote out B, because it sure looks like it's in the same direction as B, how hard would it be to figure out the negative 5 in front? Not very hard. And same thing with F. F is going in the direction of A, so I'd have 1 here. Oh, green was a bad choice. 2 of them, so F is 2 A's. And how are A and B related? If I just move A over here by itself and B over here, do they look perpendicular? You want a new word for perpendicular? Start using a new word for perpendicular in vectors. Sometimes we call them orthogonal. Why not, right? If perpendicular wasn't already weird enough of a word. So if you looked at their slopes, they are reciprocals, so they are perpendicular, and that is how you spell orthogonal. Of course, another word for slope is gradient. So let's just take every math word and create like 10 new words that mean the same thing. Because math isn't hard enough as it is, right? So I want you to try example 2. Which ones of those are parallel? And then example 3 and 4 as well. All right, you can check the answers on these. I used slopes. If you want these to be parallel, then there's going to exist some number k that one is a multiple of the other. So you could set it up, put the k out in front of these two, and from the top one you could solve for k, and then from the bottom one you could figure out t. Here's another way you could figure it out. You could say, I know the gradient or the slope of the vector r, here's the slope of the vectors s, they have to be equal, so I just solve that equation and solve for t that way as well. Last question for the day. So again, if they're parallel, one is a multiple of the other. So I set things up, which would give me 3 separate equations. T is equal to 5k, negative 5 is equal to k, and 8 is equal to sk. One of those is really good for figuring out what k is. Oh, maybe the one where negative 5 is equal to k? So then k is equal to negative 5. And then you could take another equation, figure out what t is, and the last equation and figure out what s is. That's where we'll end for today.